So we are very fortunate to have marine geochemist Evan Solomon to visit us and to give today's seminar talk. Evan is currently a professor at School of Oceanography at University of Washington, and he got his bachelor degree from University of Nevada, Reno, and his PhD from Scripps Institution of Oceanography at UCSD. And after an NRC postdoc also at Scripps, he joined University of Washington, and he has been there since then. So Evan's research is really interdisciplinary, and he combines field observations like geological, geochemical, geophysical observations, and microbiology too, and with modeling. And he has broad research interest and has done excellent work the fluids in chemical and thermal evolution of subduction zones, passive margins, and ridge flanks, gas hydrate and environmental change and cold seeps and hydrocarbon flux to the ocean and atmosphere. And he has led numerous offshore field programs around the world, including offshore New Zealand and Cascadia, Puerto Rico, and in the Gulf of Mexico. So today we will be hearing from him his recent work on the fluid flow of the Hikurangi margin, right? Mainly from the recent Saffron's experiment. So without further ado, take it away.
Thank you very much, Shuoshuo, and thanks for inviting me, and thanks for the nice introduction. So this is the talk title that I provided Constantino, I don't know, a couple of weeks ago. I was being overly ambitious, thinking I could talk about 2 subduction zones in one talk. So if people are here to hear about Cascadia, I really apologize, and I hope I can come back and talk about Cascadia again. Oh, everything's switched because it was on a Mac, but it's supposed to have an X over Cascadia. And so I'm only going to be able to talk about the Hikurangi subduction zone today, and the work that we've been doing there. So I apologize for the Cascadia folks if there are Cascadia folks here. All right, so I'm going to talk about the geochemical constraints on forearc dewatering and infer megathrust pore fluid overpressure at the Hikurangi subduction zone. I have a picture of the JOIDES resolution here because even though a lot of what I'm going to show you is stuff that we've done with surface sampling, without having ocean drilling program sites in these locations, it'd be very hard to interpret our data set. And so it's been very instrumental. So co-authors, most of what I'm presenting is a PhD thesis from a graduate student in my lab, Irita Aylward. She's also made most of these slides. And so this is largely her work, but also Rob Harris, Marta Torres, Jess Homan, Laura Wallace, and Luo is my geochemist partner on the drill ship, and Sarah Seabrook. And these, what I'm presenting come from 2 cruises that we had in New Zealand, Saffron's 1 and Saffron's 2 expeditions, but also some results from Expedition 375 of the drilling program. And funding largely comes from the National Science Foundation. Okay, so Saffron's, the title of the project was Slow Slip and Fluid Flow Response Offshore New Zealand. And the primary objective of these 2 expeditions was to test the interrelationships among fluid production, fluid flow, and slow slip at subduction zones. And we did that using kind of a nested approach in the field where, there's the laser, where we had pre-existing information of where we had seep sites, we had seismic data indicate where fault zones were, and then we did a bunch of heat flow transects to try to understand fluid distribution. Once we had that, then we would do sediment coring and use those sediment cores and the pore fluids and those sediment cores to say something about flow rates and where the fluids are coming from. And then at select locations, we deployed long-term benthic fluid flow meters. These are shown here to make continuous measurements of fluid flow rates and fluid composition through a slow slip cycle. And I'm hoping to get through all of this in the talk today. Okay, so for those that are, I'm at UTIG, so you probably all know this, but for those that don't, slow slip events are a type of fault slip, and over the past 2 decades have been recognized as a very exciting type of fault slip phenomenon. It's ignited a really dynamic field in seismology and fault mechanics. And so slow slip events are part of a spectrum of fault slip. It includes millimeters to decimeters of fault slip lasting days or months. And slow slip events occur at rates intermediate between long-term plate motion and the slip velocity required to generate an earthquake. And so in this figure here, you have a lock portion of the plate boundary called the seismogenic zone, and then this transition zone is where you generate slow slip phenomenon. So if you have steady aseismic slip, you have continuous displacement across the fault zone. no increase in stress over time. The lock zone, you have a period of time where you don't have displacement, accumulating strain, increase in stress, and then you have an earthquake, big displacement, large stress drop. In the slow slip zone, it's kind of, seismogenic process, but happening quickly, where you have no displacement, and then a little bit of displacement, no displacement, a little bit of displacement. New Zealand's unique in the sense that slow slip, unlike Cascadia, where it occurs very deep, like underneath Seattle, it occurs very close to the trench, and so we can look at the phenomenon, the slow slip process and material properties in the near field. All right, out of reach of typical sampling in a subduction zone, and because it occurs so close to the trench, it's within the reach of near field observations and sampling. Okay, so slow slip in Hikurangi, there's differences between northern Hikurangi margin and the southern Hikurangi margin. Oops, this button here. Okay, so in the northern Hikurangi margin, slow slip occurs relatively shallow, as I just mentioned. So the deformation front is here. This is inversion of one of the slow slip events that occurred here. You can see that it initiates kind of in the upper slope shelf region, and you have rupture out pretty close to the deformation front. This is kind of the cyclicity in slow slip and northern Hikurangi, where you can see displacement during slow slip events here, interslip-period slow slip events here. So they occur relatively regularly in the northern Hikurangi margin. In southern Hikurangi, slow slip occurs very deep. There's interseismic coupling out here in the slope region out towards the deformation front, and slow slip occurs deep within the system, and slow slip events do not occur as regularly in the southern Hikurangi margin. All right. Because of this, there's been a really big focused effort to understand the mechanisms and processes that drive slow slip in the northern Hikurangi margin, like I said, because we can make near field determinations close to the source of slow slip. All right, so factors that influence slow slip occurrence. In this image here, this is kind of a picture of what it looks like in the northern Hikurangi margin. And this is a picture of what it looks like in the southern Hikurangi margin. We're focusing on northern Hikurangi, where you may have some interseismic coupling towards the deformation front, and slow slip events occur pretty close to the trench. All right, and slow slip has been shown from laboratory studies and modeling studies to be influenced by a variety of different things: frictional properties, the fault zone, low effective stress linked to elevated pore fluid pressure, incoming plate roughness, and multi-scale lithologic heterogeneities. All right, and all of these things can influence slow slip. In this project, we're looking at one process in particular to try to get a better understanding of how effective stress evolves along the plate boundary of the northern Hikurangi margin. And so I'm going to focus on effective stress linked to elevated pore fluid pressure and what the hydrologic system looks like in the northern Hikurangi margin. All right. So when looking at subduction zone, fluid production and fluid flow, basically, the evolution of pore fluid pressure is a balance between fluid sources and fluid drainage, right? So if fluid drainage outpaces fluid sources, then you don't have very high pore fluid pressures. If drainage is slow compared to fluid production, then you can start generating elevated pore fluid pressures. And so this is a figure from a paper in 2001 from Demian Saffer and Casey Moore for the, wrong button. For the Nankai subduction zone, showing different processes that generate fluids and different reactions that occur within the transition from aseismic slip on the plate boundary to coseismic earthquake slip. Okay, and so what you see right off the bat is porosity decreases really quickly in the shallow part of the subduction zone. And that decrease in porosity is a fluid source term, right? And so you're driving fluid out of the pore spaces of the sediments. And so this is the largest water source in the outer forearc of most subduction zones. Okay. In addition to that, in this aseismic to seismic transition, you can see that there's smectite, clay mineral going to illite. The conversion of smectite to illite also releases water, and it's delayed compared to porosity reduction. So you start losing porosity early on. The conversion of smectite to illite happens at an elevated temperature, usually between about 60 degrees and 200 degrees Celsius. And so you get another stage of pulse of fluids a little bit deeper when you start losing water from compaction. Okay. The combination of these two things starts to drive up pore fluid pressure, which is shown here as lambda star. And lambda star is the modified pore pressure ratio, which is shown by this equation here. Okay. So as you get deeper into the forearc, you're producing water from compaction, and then permeability is getting lower and lower because of compaction. Then you start adding water from smectite to illite dehydration. Because the permeabilities are low, you start increasing pore fluid pressure. And in many cases, the pore fluid pressures are modeled to be quite high along the plate boundary. And they're higher in the aseismic region than they are in the seismogenic region, indicating that pore fluid pressure has a fundamental control on the transition from aseismic sliding to coseismic sliding. Right? There's a variety of other different kinds of reactions that occur. You're precipitating carbonates and clays, and you start getting quartz cementation that affects the physical properties of the material within the seismogenic zone. But a very important pattern, or very important control, is this generation of elevated pore fluid pressures in the outer forearc region, in the region of aseismic to coseismic slope. Okay, so that fluid is being produced and you're driving up pore fluid pressure, then drives fluid flow, right? If you have a pressure gradient, you have some permeability and the fluid's gonna move from one place to the other. And so the matrix, wrong button again, sorry. The matrix permeability within the outer forearc is usually relatively low, particularly in places like, let's say, Central America, where it's mostly hemipelagic muds. The permeabilities are quite low, but fault zones have elevated permeability relative to the matrix permeability. And so you can see these arrows going along the fault zones in this figure, okay? And so as you're generating fluids, because of compaction, smectite to illite transition, and pore pressure starting to increase, fluids will preferentially move along these fault zones because they have a higher permeability. And oftentimes we have seep sites sitting right above where the fault zones intersect the seafloor, and they're the seafloor manifestation of fluid flow along these fault zones from depth, okay? There's still fluid migration in the intergranular space in the matrix, okay, but it's at a much lower rate typically than what we see along the fault zones because of that elevated permeability. All right, there's some question on whether or not we also have up-dip migration of fluids along the igneous crust and things like that because it's even more permeable that I'm not going to get into today. Okay, so again, pore pressure along the plate boundaries as these sediments are becoming under thrust are really the balance between fluid production from compaction and mineral dehydration and the export of that fluid or dewatering of that fluid through the outer forearc, largely in many subduction zones guided by fault zones because they have an elevated permeability. Oh, let me say one last thing. Nah, that's fine. Okay. All right. So when fluid inputs outpace fluid flow, then you start generating high pore fluid pressures, and that reduces fault strength. Okay, and I think again I'm at UTIG, so most people probably know this. So pore fluid pressure reduces the effective normal stress, and so the effective normal stress is here. It's the normal stress on the plane minus the pore fluid pressure. So the higher the pore fluid pressure, the lower the effective normal stress. If your rate of fluid input, compaction and smectite dehydration greatly outpaces fluid flow, then you start really reducing the effective stress. Right, the effective stress then weakens the fault. The shear stress is here. It's a function of cohesion, the effective normal stress, and the coefficient of friction of the material. So as pore fluid pressure increases, the effective normal stress decreases, and the shear stress will decrease. Okay, so if you have an increased pore fluid pressure, you get a reduced effective normal stress, you get a reduced shear stress, and you get a weaker fault. Okay. And in many subduction zones, that transition from aseismic sliding to what we consider the seismogenic zone tends to coincide where you have a drop in pore fluid pressure, indicating you have an increase in effective normal stress. Okay, and so there's some really great models of subduction zone hydrogeology using different parameterization for fault zone permeability versus matrix permeability. And I'm going to highlight this model from Soon et al. In 2020. And I'm going to use this as kind of our base case of what we expect if we go out to a fault zone in the outer fork of the subduction zone. What do we expect to see in terms of flow rate based on what we know about the permeability structure of the outer fork? I always want to point here, not here. So in this particular model, and this is I'm going to call the background model or the base case, okay, from the Soon paper. Fault zone permeability is enhanced by a factor of 1,000 above matrix permeability. And so this is the geometry here. So this is the plate boundary. This is the incoming sediment section. And this is the outer forearc. The regions that not dark gray is the matrix, and the regions that are dark gray are the fault zones. And the shading is the permeability. And so they enhance the permeability of the fault zones about 1,000 times above the matrix permeability in this background model or base case model. And that's consistent with measurements that have been made of fault zone permeability, either from material that's been collected from ocean drilling or from modeling results based on in situ data. All right, so you have progressive landward sediment porosity reduction due to subduction of that plate. So as you subduct the plate is being buried under the outer forearc, and so it drives compaction. And due to flow along splay faults, the pore pressure ratio at the base of the wedge remains relatively low in this base case. Okay, and so you can see the modified pore pressure ratio here. Right, because you're draining that fluid along these fault zones, pore fluid pressures don't get up to lithostatic. They're actually relatively low. Okay, and the fluid flow that you observe along the fault zones are on the order. The rates are on the order of 1 to 10 centimeters per year, whereas fluid flow rates in the matrix sediments are much less than a centimeter per year. Okay, so those fault zones are really guiding fluid flow and really guiding dewatering of the megathrust and underthrust sediments in a typical model or a typical subduction zone. Is that making sense? Okay, all right. So what we'd expect to see if we go out and we make measurements of fluid flow along fault zones, we expect to see flow rates on the order of 1 to 10 centimeters per year in a typical case where the fault zone permeability is enhanced above matrix permeability. Making measurements of fluid flow along fault zones in the outer forearc is very challenging. Okay, we can do that looking at profiles from ODP cores, but we don't get to drill very often. We can try to install instrumentation within fault zones and make measurements in situ, which is also very challenging. And so there aren't that many measurements of fluid flow rates along fault zones within subduction zones. Most of what we have is model results or stuff from seismic attributes and seismic reflection imaging. Okay, and so we're fortunate in Hikurangi to have a drilling transect. And so in 2018, we cored a series of sites along this seismic line. This is a slip inversion for a slow slip event that occurred. I think this is the 2005 slow slip event off of Gisborne, showing where slow slip initiates and where you can resolve slip along the megathrust. And this transect drilled a site on the incoming plate, and then two sites on the incoming plate, and then 2 sites in the forearc as well. All right, and so this is that seismic line with the ODP drill sites. Site 1520, I'm going to talk about quite a bit. This is our input reference section. We cored through sediments into volcaniclastic sediments at the base. All right, that's what's being subducted. Site 1518 drilled through what is called the Papaku fault, which is here. We penetrated the Papaku fault and got into the footwall. I'll talk a bit about the chemistry here. We also installed a long-term hydrogeologic observatory here, which I'm not going to talk about today, but maybe Demian will. And then we cored site 1519, which is above the source region of slow slip. So slow slip starts around here. This site is above that to measure pore pressure, temperature, and also understand the properties of the material above the source region of slow slip. So the sites I'm going to talk about the most is 1520, which is the incoming sediment section, and site 1518, which is the Papaku fault in the forearc. All right, so from older studies, there's evidence of high pore fluid pressure that deviates from the reference model in the source region of slow slip. And so this is a paper from Becky Bell in 2010. You can see here, plate boundary is here, okay? This is kind of the flank of a seamount that is subducting. As I got to see really great today from Nathan, the bulk of the seamount is north of this transect. There's a flank here, and there's a region of high reflectivity landward of where the seamount is, which indicates that it's anomalous velocity and more poorly drained, which would indicate that it's higher pore fluid pressure within that region. And this happens to be the region where slow slip initiates within the northern Hikurangi subduction zone. So based on that inference, it was thought that one of the dominant controls on initiation of slow slip in northern Hikurangi was the development of pore fluid overpressure in that region. These are model results from Susan Ellis based on this initial inference showing pore fluid overpressure in the underthrust sediment. So this is the plate boundary here. Pore pressure is the contours here, and this is where the seamount is. That zone of low reflectivity in the models also shows that you have elevated pore fluid pressure. This is not the pore pressure ratio. This is just above hydrostatic. And then all these arrows are what you would expect the flow rates to be. Okay, and so you see that along the plate boundary, the modeled flow rates are quite high, and out here towards the deformation front, as well as the splay faults, that you're getting velocities on the order of 4 centimeters per year or so in this particular model. All right, so in the model, the permeability de Coleman is reduced at depth. They force it to be that way. And by doing that, it restricts drainage landward of the seamount, giving you overpressure, which is consistent with the seismic reflection data. Okay, so what we wanted to do is go and test this and say whether or not, we see what we typically expect for a subduction zone, whether or not we see evidence that there is lack of drainage within the northern Hikurangi margin, and there is development of significant overpressures within the plate boundary, and does that, coincide with where we see the high reflectivity zone and where slow slip is initiating within this margin. And so the way that we did that, as I mentioned before, is we collected a bunch of cores in matrix sediments, also at seep sites that are co-located with fault zones. And we use the pore fluid composition to estimate fluid source, or not estimate, to determine where the fluids are coming from, what the rate of fluid flow is. And by having this from the deformation front to the outer shelf in the northern Hikurangi margin, then we get an idea of the drainage pattern. Okay, so the way that this works, I want to highlight that again, just to hammer that home. This was pretty phenomenal. So we did this at the southern and northern Hikurangi margin, where we collected over 100 piston cores and gravity cores, targeting these fault zones and seep sites associated with these fault zones and off-fault locations, not just in one little postage stamp, but really going from the deformation front all the way out to the outer shelf. And so it was a really, really big coring operation, trying to address this question: what are the patterns of drainage and rate of drainage within the northern Hikurangi subduction zone? All right, so the way it works for looking at fluid sources is that fluids from different sources or different depths within the outer forearc have different fluid compositions. So in this particular example, this is not from Hikurangi, but this is a core that was collected at a seep in the Costa Rica margin, and this is a chloride concentration profile. You can see that you have curvature in this chloride concentration profile, and the chloride concentrations at depth are really, really low. Seawater composition is sitting here. Here, chloride concentrations are low, indicating that it's diluted by a freshened fluid. And that freshened fluid is because of clay dehydration at depth. So if we see something like this, and we look at the composition, and we know something about how material changes as a function of depth within the subduction zone, we can say that that fluid is migrating from this source depth. And so in this case, we have this kind of profile. It must be coming from the underthrust section where clays are dehydrating and then migrating along the fault zone up to the seep site at the seafloor. Conversely, if we see fluids that have just seawater composition, we know that the source of that fluid has to be shallow. It has not experienced these high temperatures that exist deeper within the subduction zone, and is indicating drainage of the upper part of the sediment section. And if we don't see any curve, well, this one doesn't have any boundary conditions. So anyway, that's how we use the fluid source, is to say something about the depth and temperature from where the fluids come from. We can use the shape of the pore water profiles to say whether or not we have diffusion or there's advection of that fluid. So if you have a profile that's straight up and down, we know that there's no reaction, there's nothing going on that's going to drive diffusion, and so it's a very static system. If you have a change in concentration with depth, but it's linear, then it's diffusive in nature. And so solutes are diffusing, but the water is not carrying solutes with it. And if we see curvature in the profile and it's concave down, and the solute that we're looking at is unreactive, then we know it's an advective system. And the degree of curvature can be modeled to calculate what the rate of fluid flow is. And so this is an example of an upward advective solute profile. And if it's concave downwards and it's a conservative solute, then we know that there's downward fluid flow, fluids moving from the ocean into the sediment column. So we can use the pore water profiles to say where the fluids are coming from and at which rate the water is moving. All right, so hypothesis from the Saffron's expedition, the first one was in 2019, was that if the plate boundary is draining, we would expect altered fluid compositions reflecting sediment fluid reaction at the base of the wedge and the underthrust sediments. Those fluids, the water that's being subducted with the downgoing slab. And if the plate boundary is overpressured and not draining, then we would expect much less altered fluid compositions, reflecting fluid sediment reaction in the upper wedge of the sediments, but no contribution of dewatering from deeper within the system. All right. And so these are our coring sites in the southern and northern Hikurangi margin. So here's the northern Hikurangi margin. We basically were confined to the Expedition 375 transect, and we took cores in all these different locations. There was work done by New Zealand scientists before we planned this expedition, looking at the distribution of all the seep sites and seep indicators along the Hikurangi margin and tying them to seismic reflection profiles. So we already knew where to go before we went out to sea. We collected additional information, different hydroacoustic surveys, to identify new seep sites that were not in the compilation, but we had a really robust compilation of seep locations in the northern Hikurangi margin before we actually went out to sea. All right, and so we basically targeted seep locations that are tied to fault zones going from the deformation front to the outer shelf, and cored all those locations in both the northern Hikurangi margin and the southern Hikurangi margin. And for those that study Hikurangi, we were kind of close to the Sake line for the southern Hikurangi margin. All right, and so doing that, we used that previous, seep compilation to guide where we collected these cores, and we collected gravity and piston cores at all these different locations, as well as non-seep locations for control sites. All right, and this is our sites in plan view. So northern Hikurangi margin sites are here. Okay, and so I'm going to say HFA north, and those are sites that are closer to the deformation front. Site 1N, 6N, and so forth. Okay, and so moving from the deformation front to the upper slope. And in the southern margin, we had off seep locations, but also a variety of seeps tied to thrust faults within the wedge. There's color coding here, but we collected a ton of gravity and piston cores. We also did these heat flow transects as well that guided our coring activities. And then the stars are locations of long-term installations of fluid flow meters that I'll talk about at the end of this talk. Okay, so we collected over 80 sediment cores. It was actually 100 to determine fluid composition and rates of expulsion. We collected gravity cores and piston cores up to about 10 meters in length. Pretty tough to core seep sites, and so it requires patience. And we also collected push cores using ROV Jason. So we do kind of broad scale gravity and piston coring from the ship, and then we use the ROV to investigate those seep sites and collect targeted cores at the seafloor using push cores. Once we get the core, the way it works for geochemistry is we have to basically cut out sections of that core, extrude that sediment. We then squeeze the sediment in a squeezer. And so this is a titanium squeezer and a hydraulic press. We push the water through a bunch of filters, get the water from the interstitial space of the sediments, and we get our pore water samples. And then on ship, because we're usually constrained for time, we only make a measurement of salinity, and then we do an alkalinity titration on board the ship. And that's because alkalinity is a transient measurement. Based on those initial measurements that we made at sea, we chose 26 representative cores for further geochemical analyses. And we focused our analyses on the major and minor elements. So looking at calcium, magnesium, sodium, et cetera, as well as some of the minors. And ammonium is actually quite important too, because we use it for modeling flow rates in this particular study. All right, so what do these profiles look like? I'm just going to give you some examples. Again, there was 26 cores, so I'm not going to go through all of them. But what we see is cores where we don't have any fluid flow when we're outside of a fault-hosted seep site, and then cores where we have fluid flow when we're at a fault-hosted seep site. All right, and so this is a background core. This was BB71 collected on the upper part of the slope. And you can see that there's no deviation in concentration of things like chloride or strontium as a function of depth. Okay, this is a place where we do not have fluid advection, and it's the diffusional system. Once we go to a fault-hosted seep site, then you start seeing curvature within the pore water profiles, indicative of fluid transport from depth. Okay, so we can use those shapes of the profiles to calculate flow rates, and we can use the composition that we see at the base of those cores to say something about the fluid source. All right, so we use the pore water geochemistry to determine the source of the fluid. Again, it's based on its concentration, and we look at the periodic table to determine that, and our knowledge of fluid and sediment reactions is a function of temperature. And we use the shape of those pore water profiles to calculate the fluid flow rate. First, I'm going to talk about the source of the fluids that we see draining or migrating along the fault zones within the northern Hikurangi margin. Okay, so as I mentioned before, I'm going to use 1520 as our reference location. So site 1520 is here. This is the basal part of what we cored. And there are two units or three units that I'm going to focus on at the base of the section. These are the units that are subducting or are at the base of the wedge, just above the plate boundary in the northern Hikurangi subduction zone. So unit 4 is a marl. Right? The calcite content of is quite high within this unit. It's pelagic in nature. Low sedimentation rates. And at the base of unit 4, then we get into volcaniclastic sediments. And I'm sure many of you guys have heard about these volcaniclastic sediments from other talks. But it was quite a thick section of volcaniclastic material. And when we go into the volcaniclastics, they've altered over time to clay minerals. They're very smectite and zeolite rich. Okay. Carbonates, no, right? There's not very much clay minerals within the carbonates, and so there's some smectite. But once you go into volcaniclastics, it becomes a smectite-rich sediment, very clay-rich, due to alteration of that volcaniclastic material. As that plate is subducted and that volcaniclastic sediments go down into the subduction zone below the plate boundary, the temperature increases, and at a certain depth, the temperatures reach the temperature where smectite starts to dehydrate and water is released. So we expect large degree of water production at depth from this unit due to clay dehydration. So where would that occur based on what we know about the thermal structure of the northern Hikurangi margin? The temperature range of clay dehydrations around, peak clay dehydrations around 50 to 150 degrees Celsius. This is a model on Transient et al. 2019 based on surface heat flow values, but it's a thermal model. And the preferred model result is this black line. And so if you go and look at where 50 degrees to 150 degrees sits at the plate boundary, we're sitting here and here. Okay, so this field here is the field of peak clay dehydration based on what we know about the thermal structure. Where we sampled, so our sites in the outer forearc where we collected cores, sit here. Okay, so most of our sites sit above the region where we would expect to have clay dehydration. If clays are dehydrating, you're adding fresh water to the system, and so that's going to dilute the pore water, and our chloride concentrations will be low if they're being sourced from if the fluids are being sourced from the underthrust sediments in that region, migrating along the fault zones, and are emitted at the seep at the seafloor. All right, so we have clay-rich sediments in the volcaniclastic unit, which is most of what is being subducted. It's very thick. The temperatures are what you would expect for clay dehydration, so we'd expect to see a low chloride signature in all of our seep sites that are above that region. All right, so just to hammer that in again, this is what we observe, or what has been observed in Costa Rica, where we have a lot of long-range transport along fault zones. Chloride concentration at those seep sites is really low. It's dilute. There's a lot of fresh water being added to the system, and that fluid is migrating along those fault zones up to the seafloor where we sample it. This is what we observe at basically all of our seep locations, not basically, all of our seep locations in the northern Hikurangi margin. No evidence of dilute fluids migrating along the fault zones to the surface. Chloride concentrations are basically seawater concentration or greater at every single one of those fault-hosted seep sites. Okay, greater because there's quite a lot of volcanic ash alteration that occurs in the sediment section that increases chloride a little bit, but we don't see any evidence of dilute fluids. Okay, what we would expect if there was long-range transport of fluids is what I just said, is that you would have this this low chloride signature. This low chloride signature in our seep sites. But we were also fortunate enough to sample site 1518, the Papaku Fault, from drilling. And we penetrated the Papaku Fault at 300 meters below seafloor. So that's here. So site 1518 penetrated the Papaku Fault. If there was fluid transport along the Papaku Fault, draining fluids from the plate boundary, it would have a low chloride signature. Okay, this is definitely within the range of clay dehydration. We sampled that fault zone at depth. And what we would expect is something like this is what we see in Costa Rica. This site 1254 penetrates the plate boundary here. And we have these big signals of lithium increases due to high temperature fluids coming from depth. Chloride concentrations are depleted. This is a thrust fault sitting above the plate boundary, but chloride concentrations are depleted in the plate boundary. We have the presence of thermogenic gas, all indicating long-range transport along the plate boundary from temperatures that are much, much deeper than where we're sampling. In this case, the fluid transport is about 12 kilometers distance. Okay. What we see at site 1518 is no evidence of anything. It has to do with fluid flow occurring within the Papaku Fault. So the gray shaded area is the Papaku Fault, and these are chloride concentrations here. Okay, so chloride increases slightly above the fault zone, and we see a little bit of a trend of chloride below that, but this isn't because of advection. This is purely a diffusional profile across that fault zone. We don't see any enrichment in lithium or strontium or anything along the fault zone. There's no geochemical indication from what we drilled at site 1518 to suggest that there's migration of fluids from depth along the Papaku Fault, which is basically what we see at every seep site that we cored associated with all the faults in the northern Hikurangi margin. So there's no geochemical evidence of fluid flow along the fault zone at site 1518. Furthermore, if there is local upward advection of water from the underthrust sediments below that fault zone into the fault zone, we see curvature of the profiles below that fault zone, and we don't see that either. Chloride's linear below the Papaku Fault, And actually, we're doing some modeling work on that, and it's basically diffusional communication since those sediments were under thrust. So there's no evidence of a long-range transport along any of the fault zones, either from our seep survey or from drilling. Okay, just to hammer that in, we also have another tracer besides looking at dehydration-derived fluids. We can also look at drainage or fluids that are coming from Unit 4. And this is a really powerful tracer in the Hikurangi setting. So this is Unit 4 here, and this is strontium concentrations on the x-axis. Unit 4 is that carbonate-rich sedimentary package. Okay, and Unit 4 kind of sits at the right at the top of the megathrust in the northern Hikurangi subduction zone. Because it's carbonate rich, it's recrystallizing over time. And it's going from basically a aragonite calcite composition to a more dolomitic composition. And in doing so, strontium is kicked out of the mineral structure and added to the fluid. Right? Seawater strontium concentrations are 87 micromolar. The strontium concentrations within Unit 4 are up to 1,500 micromolar. And over time, that concentration would continue to increase. As we go into the volcaniclastic strontium, we're back down at seawater value. So you have this packet of sediment that's relatively thick, that has very high strontium concentrations. And so if we were expect to have fluids draining from Unit 4 within the subduction zone, we would expect to see strontium signal at the seafloor, okay, in our seep sites. These are cross plots this is a cross plot of lithium versus strontium. And these are the different units that are subducting. So these are the units at site 1520, and these are their kind of average lithium and strontium concentration. So this is Unit 4 here. And you see the strontium concentration is really high. This is Unit 3, it has a very high lithium concentration, and this is the volcaniclastic unit. These red triangles are the fluids that we collected at the fault-hosted seep sites, and none of them fall along a trend to Unit 3, Unit 4, or Unit 5. They bounce around Unit 1 and 2. So there's no evidence of fluids that have come from Unit 4 at these seep sites. Okay, and even if there was just a 10% signal in strontium, this is the strontium concentration that we'd observe, and we do not see that. Okay, and if there was just a little bit of volcaniclastic fluid coming in, we'd start to see that in our trends as well. And so these do not fall on mixing lines whatsoever, and our fluids look like they're being sourced largely from the very upper part of the sediment section. Okay, we can do the same thing with magnesium and calcium. All right, again, Unit 4 is here. This is the carbonate unit. This is the volcaniclastic unit. All of our seep fluids plot along kind of a mixing line from seawater to Unit 2. We do not see any mixing with Unit 4 and Unit 5. Okay, so no contribution from those lower units in the fluids that we observe in the seeps. In the same case for the Papaku Fault at site 1518. Okay, oh, that's what I say. So there's also no evidence of underthrust fluids migrating along the Papaku Fault. Strontium concentrations are, just about seawater. No elevated strontium, no peak in lithium concentrations within the fault zone or above the fault zone as well. Okay, so based on the pore water geochemistry that we collected on Seafloor, as well as IODP Expedition 375, we can say that the source of the fluid migrating along the fault zones that extend down to the megathrust is shallowly sourced, all right? And it's sourced from compaction in the upper wedge, but not draining the deeper part of the wedge, nor draining the megathrust, okay, or the underthrust section. Okay, all right, and that's both ODP drilling and all of our piston cores. Now we can look at what the flow rate, and we can get that from the shape of the pore water solute profiles. Right, and so we can use reactive transport models to look at to use the pore water solute profiles to calculate a flow rate. And so this is the equation here. Our model is kind of sophisticated. We can have a varying upper boundary condition. We look at compaction. We look at change in porosity. We look at pore water burial. We can look at reaction rates, et cetera, to model the flow rates. Right, and so these are some examples from one of our cores. JPC01, where we get a flow rate estimate between about 0.1 and 0.5 centimeters per year upward. This is more for geochemistry folks, but with these short cores, we don't have a bottom boundary condition. Ammonium's continue to increase, everything's continuing to increase, they're short cores. All right, we're fortunate that we had ODP drilling where we have a much longer sediment section where we have a better bottom boundary condition. And so what we did is something very similar to what the heat flow community does, is we use site 1518 and 1519, knowing there's no upward advection to calculate reaction rates. And then we made synthetic models for our locations that are around them for upward advection rate, looking at just the very upper part of the sediment section. And so this is the ammonium profile at site 1518. Okay, and so we focus on the upper part of the hanging wall. We say there's no fluid flow, upward fluid flow at that site, so we can get reaction rate for ammonium production. And then for our locations, we then, use that synthetic or that, calculated profile to run synthetic profiles at different advection rates to see how our little tiny cores that are just at the very sediment, the very close to the sediment water interface fall along those lines, right? And so this is a upward advection rate of 1 centimeter per year. This is 0.1 centimeters per year. This is site 1518, and these are some of our cores here, okay? So we have upward advection at these sites, but it's not super high. We're looking at pretty relatively low rates of upward fluid advection. And so these are our results as a function of distance from the deformation front. Okay, so flow rates on the y-axis, and this is distance on the x-axis. We have the highest flow rates that we observe right at the deformation front, and then relatively low as you go seaward of the deformation front. And these are all those fault-hosted seep sites. All right, so a lot of them are very close to diffusional, just a little bit elevated, but in general are kind of sitting below 1 centimeter per year. All right. So flow rates of fault-hosted seep sites are lower than predicted by reference models of subduction zone hydrogeology. Those models where the fault zone has an elevated permeability over the matrix permeability. We'd expect flow rates on the order of 10 centimeters per year if fault zone permeability was enhanced. Right. At the northern margin, flow rates are highest at the deformation front, but relatively low in general. Okay. The southern margin, which I'm not showing here, much higher flow rates in general. In some cases, we get flow rates up to 50 centimeters per year in the southern Hikurangi margin. But in the northern Hikurangi margin, the flow rates are really low and much lower than we would predict if the fault zones were more permeable than the matrix sediments. And that's what I show here. All right, so we can compare our flow results to those of the models. This is that reference model I showed earlier where the fault zone permeability is 1,000 times enhanced for matrix permeability. And we're getting flow rates on the order of 8 to 10 centimeters per year along these fault zones. All right. Our results are more compatible with those models where the fault zone permeability is not greatly enhanced. So you can see here, we got fault zone permeabilities enhanced to 10 to the minus 13th meters squared. In this case, they're more similar to matrix permeability. And in those models, the estimated flow or the predicted flow rates along fault zones are 1 centimeter per year or less. And that's exactly what we're measuring in northern Hikurangi. All right, so we have two observations now: a lack of a geochemical signal of plate boundary fluids. All right, we don't see fluids migrating from a long distance; they're being sourced very shallow, and we have flow rates that are very low, much lower than we would predict from models where you have elevated fault zone permeability. All right, and that's consistent with the lack of no signal of fault-hosted flow from depth, okay, or from megathrust-hosted flow from depth. All right, one last thing I want to add to this, just a little wrinkle, is that at these low flow rates, the transport distance along those splay faults from the plate boundary is pretty long. And so the question is, are we not seeing a signal of drainage of the underthrust section because of diffusional loss along that long transport distance? Okay. And so the question is, could there be a loss of our geochemical signal due to diffusional loss along that fault zone, along its flow path? And so we generated a range of different models to test this, but we're using strontium, saying, okay, would we retain a signal of that strontium concentration we see in unit 4 if that was dewatering and that fluid was migrating to the seafloor? We use a bottom strontium concentration of 1,300 micromolar. We use a flow rate of 1.5 centimeters per year, which is kind of on average of what we see. And we run these models to steady state. These are the different fault zones that we model: 1, 2, 6, and 8, and these are the profiles. These aren't as good as with the new 3D seismic data set, okay? But this is basically what we would get in the strontium concentration profile at that flow rate for those different fault zones. Okay, so short fault zone, we still see a really strong signal within the depth range that we're sampling close to the seafloor. So our cores get to 10 meters depth. We still see a strontium concentration of 900 micromolar. So we would still see that signal. Longer fault zone like site 6, we still would see a very strong signal of unit 4 dewatering. It isn't until you get to a very long fault path where we may have complete diffusional loss and there would be drainage from the plate boundary. We don't see it because it's diffused away, okay? And that would be the case of fault zone 8. That ends up being around 9 kilometers or 10 kilometers transport distance at these flow rates, okay? The reason I present this is that we're convinced that if the plate boundary was draining, we would see it, okay? Even at these low flow rates, we would not diffuse it all away, right? We just simply don't see it. So we retain the underthrust signal. All right, I want to compare what we see in the offshore seeps with what has been observed in the onshore seeps. And this is work that was done by Jamie Barnes here at UT. And so I'm focusing on those onshore seep sites, which are shown here in the northern part of the Hikurangi margin, same region that we're looking at, okay? The onshore seep data is here in black dots, okay, and our data is down here, all right, next to seawater, okay. You can see the trend in the onshore seep data trends towards unit 4, kind of like what I was predicting, what I was thinking we would see in the offshore sites. And some of those onshore seep sites have really, really high lithium concentrations. But the trend in the onshore seep chemistry reflects greatly what the underthrust fluid chemistry is, okay, and the incoming plate. What happens in Hikurangi is in the offshore part of the forearc, it's an under compression. And based on borehole breakouts and other techniques, when you get into the shelf environment into the onshore, it's under extension. And so the permeability structure and the type of stress environment changes from the offshore to the onshore, okay? The onshore streams are in this extensional regime, and in this extensional regime, we observe a very strong signal of deep source fluids and high fluid flow rates with strontium concentrations consistent with those in underthrust unit 4. In addition, if you look at the lithium concentrations, there's been hydrothermal experiments with smectite and subducting sediments as a function of temperature. And the lithium concentrations are, roughly what you would expect for smectite at 250 degrees Celsius. And if smectite was up at 350 degrees Celsius, this is the lithium concentration in the fluid that you would predict. At the distance from the deformation front that the onshore seeps are at, the temperature is anywhere between 250 to 350 degrees Celsius in the underthrust section of the plate boundary. Right? And so the onshore sites, when we went out to do this experiment, we were expecting to see this in the offshore sites too, right? We don't see that. We see no evidence of fluid flow, appreciable flow rates, or drainage of the plate boundary. You move into the onshore section, and you have very strong evidence that you're dewatering that underthrust section, and that's contributing to the fluid composition that's seen in these seeps. So there's effective dewatering occurring once you get into the extensional regime. Is that clear? I think that was clear. Okay. All right, so let's put this together. Okay, so the results, the fluid compositions that we have indicate that there's no high strontium, no high boron, lithium, calcium, potassium, the kinds of things that we would expect if we were seeing drainage of the underthrust section. We see really low flow rates, much lower than would be predicted if the fault zones are permeable. All right, so we're in the situation where we have shallow sources of fluid in the offshore forearc, and then you move into the onshore portion of the forearc, and we start seeing a very strong signal of deep source fluids. All right, so we have shallow fluid sources, no input from the underthrust section. This could be because of lateral drainage of those fluids. So the fluids that are, the material that's being subducted, it's being compacted, you're driving mineral dehydration, and you have simple lateral drainage potentially along the volcaniclastics. Or the underthrust section is just not draining, it's not draining vertically. In any case, you may predict that the plate boundary is overpressured. The water's not moving out of the system. Rate of drainage is less than the rate of fluid production, and you have a very overpressured megathrust, right? The reason, at least our results are showing that we have lack of vertical drainage or drainage along these fault zones is those fault zones must have really low permeability, right? Across the northern Hikurangi margin. It must not be very different than what we have in the matrix sediments. So we have low flow rates, fluids aren't draining efficiently, fault zones have relatively low permeability and probably even lower permeability at depth. We are seeing some drainage from the upper part of the wedge, right, at relatively low rates, and the source of that fluid is from the upper wedge, from the chemistry, and so there's some permeability of those fault zones closer to the seafloor, but as you get deeper within the wedge, they must have effectively a very low permeability. All right. Onshore, we have evidence of a very efficient drainage with a jump in the effective coefficient of friction along the plate boundary, which we don't see in the offshore portion. I don't want to dwell too much on that, but basically, if you're draining the plate boundary greatly on the onshore portion, then you can decrease effective stress, increase effective stress, and you might start driving an increase in the coefficient of friction. And the models require that. There's no evidence of vertical drainage consistent with the slow slip source in the offshore portion region being overpressured. And it's inconsistent with enhanced permeability due to seamount subduction, and it indicates fluid storage in the wedge potentially in northern Hikurangi. Okay, so just to review, the fault zones at depth are likely very impermeable or not as permeable as models would suggest in the northern Hikurangi margin. There could be a significant portion of lateral flow, but not very much in the vertical direction. And if you're having poor drainage, you would expect that you would have overpressured fluid within the underthrust section. Okay, so but there could be significant lateral drainage within the underthrust sediments. Unit 5 and Unit 4 is the volcaniclastic section, and even seaward of the deformation front, we have geochemical evidence of lateral flow within that section. And so before it's subducted, the volcaniclastics already are quite permeable, and they may be a preferred flow pathway for fluids leaving the forearc. All right. So this kind of, lack of drainage, this doesn't come out too well, but this kind of lack of drainage kind of shines through a little bit in the electromagnetic data that's been collected recently too. So this is data from Christine Chesley. This is a control source electromagnetic, and you see these regions of anomalous porosity preservation within the wedge. Okay, these packets that don't appear to be draining, kind of trapped in the lower wedge. And once you get to they don't extend to the seafloor. So basically, what we're seeing in the surface sampling is that we don't see any evidence of drainage of fluids. And what you see in some of this controlled source electromagnetic data is that you have storage of fluids in the lower part of the wedge, but not very efficient drainage in the upper part of the wedge. And that was also, this is a crummy figure, I apologize, observed to a certain degree in the Hawke's Bay region, which is south of where we're at, where VPVS changes greatly in these lateral packets between fault zones, indicating that you have potentially anomalous pore fluid pressure, which may indicate that fluids are being stored in the lower part of the wedge, but you don't have effective transfer along the fault zones to the upper part of the wedge. All right, so I'll leave that with that. All right, I want to spend just a few minutes, because this is really new, talking about the results from the benthic fluid flow meter experiment. So we deployed two different types of fluid flow meter. We deployed cat meters and mosquitoes. Both measure the rate of fluid flow in the vertical direction in the shallow part of the sediment section. Big difference between the two is the cat meter amplifies the flow that you are measuring, and so it has a collection chamber, and it funnels the fluid into a smaller cross-sectional diameter. And so we can measure flow rates that are like really, 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 really low with a cat meter. Mosquito is a little bit better from looking at seep sites. It measures vertical flow, but you get a vertical continuous sample of fluid composition as a function of depth. So both types were used, and we deployed both of these benthic flow meters for 2 years to measure continuous fluid flow rates and composition at both fault-hosted seeps and off-fault locations. We deployed 16 of them, right, 8 of each type. These were deployed in 2019 when we were collecting all these cores, and we recovered them in March 2021. Due to pandemic-related shipping delays, we conducted that cruise during the pandemic on the Tangaroa because we couldn't use a U.S. vessel. It was very challenging. And getting our stuff back out of New Zealand was also very challenging due to all kinds of issues related to the pandemic. We've also had some instrument issues, and so we just generated preliminary data from 2 of the cat meters, and I want to share with you. And it's very preliminary, like I got it on Tuesday. Okay, so we put mosquitoes and cat meters at a variety of locations in the northern Hikurangi margin, and the goal was to look at how fluid flow rates and composition change through the slow slip cycle. These are the locations of cats and mosquitoes. This is the southern margin, and this is the northern margin. I just zoom up in the northern margin. So we have a cat at the deformation front. This is another cat that's off of a seep site. This is a seep location. This is an off seep location. But the 2 that I have data from are 19-4 and 19-7 out here close to the deformation front. Site 1518 is about right there. Okay, so what we'd expect to see, in terms of if we had long-range transport and broad-scale changes in flow rates at these seeps during a slow slip is what has been observed in a couple of geophysical studies. Let me fast forward a little bit. No, it blacked out. Oh, there's supposed to be a figure down there. I apologize. Mac to PC conversion. But what you expect to see, due to kind of pore pressure modulated slow slip is that during the interslip period, pore pressure increases and is continuing to rise because you have fluid production. And then you have slow slip and permeability is enhanced and you have drainage of that fluid. And the fluid may drain up to the seafloor or may not. And during the interslip period, then pore pressure would increase again, effective stress would decrease until you had another slow slip event, permeability is enhanced, and you have drainage of the plate boundary. And that's kind of a sips and pumping process, and has been hypothesized to occur in these systems, and has been observed in changes in VPVS at the plate boundary during a slow slip cycle. And also burst type repeating earthquakes have been observed that during a slow slip event, you have tremor that's occurring in the upper plate, likely associated by fluid flow, and that's observed in the basically slip period, and then in the interslip period, you don't observe that any longer. And there's supposed to be a figure showing that. And so there's been some geochemical evidence of this existing, geophysical evidence of this existing in Cascadia, in Hikurangi, but it hasn't been directly measured. So we put our flow meters out to actually look just at that process, okay? And we were fortunate that a very large slow slip event occurred during our deployment period. So there's a large slow slip event that occurred between March and May 2019. This is the CGPS station on land, and you can see that you have steady displacement, and then the slow slip event occurs. It occurs around March 25th or so. Fast rate of slip, and then kind of slows down a little bit, and the slow slip event's over by around May 1st, 2019. All right, we knew that was going to happen. That's why we had our crews when we had our crews, that there was going to be a slow slip event that year, and we had our instruments out during that slow slip event. So these are our locations here, and this is an inversion model from Laura Wallace's student showing the slip patches during that 2019 slow slip event. Okay, and really quickly, I just want to run through this. So these two are fault locations. This is just tracer concentration data from those, just so you guys have an idea of what it looks like. This is where we had the slow slip event from the continuous GPS monitoring. Right? And what we see from this record is that during the first week of deployment, we have really high flow rates, and that's just due to the insertion of the instrument. To about March 12th, which is preceding the slow slip event, we have really, really high downward flow rates. Not high like centimeters per year, but high for an amplified instrument, okay? And it's likely due to extensional strain at the seep location, or at the location that this instrument was deployed. So we certainly see extensional strain preceding the slow slip event. This is the location that's on the hanging wall of the Papaku Fault. Through the slow slip event, we have downward flow, but at a rate that's slower than before the slow slip event. And then after the slow slip event, no change, right? It's just basically no flow after the slow slip event, right? And so what we're seeing at this location, which is kind of cool, we're using the flow meter as a strain meter, and we're seeing extensional strain before the slow slip event, less extensional strain during the slow slip event, and then nothing happening during after the slow slip event. And we see a very similar signal at the deformation front. And so again, this is a slow slip event from continuous GPS. We have moderate downward flow to the start of the slow slip event on March 23rd, again, likely due to extensional strain at the deformation front. Then we get much more faster downward flow at the beginning of the slow slip event, then it decreases to the end of the slow slip event, and then at the end of the SSE, it just goes to zero and there's no flow. Right? So we're certainly seeing flow transients associated with slow slip at these two locations, and the flow transients is indicating that we're under extension at these two locations, which is pretty cool. Okay, the data was just produced this week, so the interpretations are very preliminary. Stay tuned for more data as it exists, and my students can be presenting, the complete data set hopefully at HU. All right, so that's all I got for our activities at Hikurangi.
Thank you, Evan, for the excellent talk. I think we have time for a few questions. Arm?
Okay, Evan, I have a question about the nature of the permeability that you model for using the geochemical data. Does that represent permeability, for example, from an inter-slip period or averaged over all seismic cycles?
That is average over many slow slip cycles and probably at least one seismic cycle in terms of what our profiles show in the cores. To add to that, the flow meter data, which I haven't gotten to the seep sites yet, we're now analyzing now, will produce flow rates through slow slip events. So we'll be able to get a handle of how permeability might change during the slow slip events.
Thank you.
More questions?
I'll have another question then, and that is
I'll actually go back to the other one. I mean, we're looking at probably like mini seismic cycles, like 2,000 years, basically. It's kind of an average of 2,000 years from the cores.
Okay. Yeah. So when you take these samples on the surface, how does a fault as a conduit manifest itself? I mean, are you worried about sampling some permeability that is not really connected to the conduit? Is this something that is in a really small area, for example, 100 meters, or how wide is a zone where you expect to have this kind of enhanced permeability?
Yeah, so that's a good question. So they're complicated, right? Because they're seepage locations. So we try to stay away from the ones that are gas dominated because there's a lot of gas driven processes that occur at seeps. Can you hear me okay? I'm sorry. Yeah, and so what we did in these cases is try to collect at least 6 cores per seepage location over a big enough distance that we felt that we were getting a consistent result. So basically kind of like by numbers and averaging, and then our heat flow transects, which I didn't show, they show zero flow. So heat flow has no evidence of fluid advection either. Less sensitive to flow than the chemistry because of the rate of heat conduction, right? But we have no evidence. Those were kilometer long strike of the fault zone profiles that we collected.
Thank you.
We see nothing at the deformation front in the heat flow. Heat flow shows nothing.
Hi, thank you for a great talk. It's more of a question / comment. If you go back to the porosity slide derived from the resistivity.
Yeah.
Sorry for.
That's okay. This
scrolling back.
one from Christine's paper, yeah?
Yeah. So just above that conductor that you associate with your kind of extrapolation down, in 519, you have a resistor over there, which kind of it's interflect or it's disagree with your geochemistry analysis, while that conductor, I would be very careful to associate it with something deep from your, because there is a seamount and there is a lot of tilt in that formation. And this was inverted with the vertical transverse isotropy. So not accounting for the tilt, it's critical here. So it might be that might not really indicate what you're seeing in your information.
Yeah, no, I was just trying to link up kind of their observations with what we see, but that, yeah, totally. 1519 in that region, we don't have any fault-hosted seeps that we sampled. So it's kind of a region where we don't see any seafloor manifestation of.
That's what I'm saying. But if there is a resistor under it, which means if that resistor is wrong, that also been interpolated that what you're thinking is right is also wrong.
Yeah,
that's just an observation.
Have more questions? Peter.
Just wonder if you have any hypothesis for why your faults are less permeable here than, for example, Nankai. I mean, something to do with the stratigraphy that's accreted. And then related to that, you talked about a permeable volcaniclastic that could be draining this. Is there an obvious drainage path for that?
they're both really difficult questions, Pete. I'll talk about the volcaniclastics first. So all I can say about the volcaniclastic unit is that at 1520, it is hosting the lateral transport of seawater at relatively high rates, at probably a relatively low driving force. We don't have direct measurements, to my knowledge, of the permeability of the volcaniclastic units, but those are hosting, fluid flow of seawater, which I was originally interpreting as being recharged from that seamount right adjacent to 1520. So it's likely that they remain permeable as, at least at the initial stages of subduction. In terms of ventilation of that fluid, I have no idea. So all the seamounts in that region are covered by a pretty thick sediment section. There aren't outer ice faults that go into the volcaniclastics in that region either. There's one seamount that's outcropping south of the 375 transect that could be a candidate for ventilation. But if it is draining laterally along the volcaniclastics, I don't know where it goes. Heat flow, transects in the basin, the subducting sediment section do not show any evidence of fluid discharge anywhere. It's just a single transect, right? But anywhere along that transect, everything's consistent with isothermal flow in the upper part of basement and follows basement topography. So I don't know. What was the first question? Oh, why is the fault zone permeability so low? So Papaku fault has a lot of ductile type deformation. And so it could be associated with the shallow faulting behavior, potentially, of a fault like the Papaku fault. In the 3D seismic data, the fault zones have a higher seismic velocity associated with them than outside of the fault zones, which is interpreted to be the carbonate section, unit 4. Typically, I think of carbonates as being quite permeable laterally. But those carbonates were held up by grain cements, so the porosity of the carbonates at 1520 is quite high, much higher than they should be. So whether or not that cement breaks, as it's being subducted. But there is high seismic velocity associated with the fault zones at depth in the prosum. And Nathan can comment to that a little bit more if you want to chime in, but. So there's, there's evidence, but I don't know, there's no smoking gun.
All right. Let's just thank Evan again.